Okay, so this is your first live session for your NPTEL course on Advanced Quantum Mechanics with Applications for the year 2026. Uh, okay, so yeah, so I hope like you have already seen like there have been lecture videos on your portal have been uploaded. Like I think it's been week 2. You might be seeing all the videos till week 2 at least in your portal. So if you log in into your respective portals, you will find them. And also like week 3 is also on the way. So I hope you are going through the lecture videos and trying to learn this nice course. So this is very useful course, like in terms of what you want to do in future. Like for example, like it's very essential in terms of research in physics. Like it's very important, and also it's other wide applications. Whether you talk about in industries, so quantum computing and other perspectives as well. So it's important you find this course very useful. And yeah, so I hope like you will enjoy this course. And so you are finding the lectures interesting. And if there is any difficulty, like, so this is the place where we'll try to solve out those problems. So like any questions, any doubts, like please feel free. Like you are always welcome to like interrupt and ask any questions. And then yeah, so here importantly we will try to focus on some important questions, like which are uh, necessarily going to be useful for that week's topics. So for example, week 1 you have seen certain topics, and also there has been an assignment to you. So based on that, like we'll go through some problems which might help you in going through those assignments, and also understanding some concepts, and more importantly, it will help you revise the things maybe in slightly better way. So this is this live interaction, one to one. We can talk and discuss and try to resolve any issues if you feel. So yeah, yeah, so I hope you are going through the lecture videos, right? So are you able to access them? uh, Here's uh, like there's somebody trying to like record and take the notes here. But yeah, like don't worry about that. Like you'll be like getting this recorded live session. And also if any this presentation notes, whatever we will be having right here, will everything will be shared with you. So yeah, so are you all able to access your course, or you are having an issue? Like you can find the lecture videos, right? So, uh, right, or like, yeah, there's somebody want to speak something. Yeah.
Sir, I joined this course on 29th July, sir. I do not
Right.
attend the section. Can I pick
Uh,
up later?
which session? Which session do you mean? So this is the first live session. If you're talking about this live session, right?
Yes, sir.
This is our first live session. So this live session was like supposed to take place last week, like at some day, like probably around Friday or Saturday. But for some reason, like it got cancelled. So today we are having it. So and tomorrow we'll have another session. So yeah, so tomorrow will be your second live session. But yeah, this is your first live session. So yeah, you have not missed anything so far.
No, okay, sir.
Okay. So you are able to access the courses on your NPTEL portal, right? You can find the lecture videos, right? Uh, yeah. So I hope like if all of you are able to can access them. So yeah, if you have any issues, you can speak. So yeah, today like we'll basically talk about some, the some problems particularly related to the quantum mechanics course level 1. We won't go into any advanced topics in this live session, so we will keep things very basic, and also you'll find the assignment problems to be quite best like that, so you will find it bit easier. I hope at least all of you have done some level, some basic level of quantum mechanics course before. So if not, that is fine. You can still go through the lectures in the first week, which is given to you. And also, if you are missing out some important basic details, you can find out some standard books and standard notes. And yeah, of course, we are here to discuss them as well. So feel free if you are unable to catch anything anywhere in our discussion. So so we'll basically talk about some some uh, basic quantum mechanics mechanical problems. So um, okay. So if anything else, somebody wants to say something, please uh, let me know, or we can uh, move on with today's problems. Okay, so I hope things are fine with you at the moment for you. Uh, we'll start with a very fundamental problem of quantum mechanics. It is the starting problem that everyone likes to do. So it is on infinite potential well. So what we have? So um, we have a particle which is trapped, a particle of mass n, which is trapped inside a infinite square well potential. So that potential is given to be of this form. So you can write mathematically this potential for certain length. So we are considering only one dimensional system. So you will find from uh, some point at the start to the end, you will find the potential to be completely zero, and rest of the reason, you will have the potential to be very high, something infinite, you can say. So so if I draw this potential, so it would something uh, like would look like this. So this is, let's say, the x-axis, and suppose if this is x equals to 0, why does it have cube? Yeah, you are right. You can say, here I am also telling it to be a square. Maybe for one dimension it is not necessary, uh, but this infinite weight potential in general, in practice, it can be three dimensional. So which is actually three dimensional in actual practice. So if that is three dimensional, so when we are talking about three dimensional infinite well, then we have to specify whether it is a square type three dimensional well or rectangular type three dimensional well. Because if it is a square, or otherwise cubical square well, which you mean basically. So if I have for example, yeah, so if I have something like a three dimensional infinite well, so it would be uh, uh, either cube or rectangular. So if it is cubical type three dimensional infinite well, so your potential would be something like Vx. It would depend on all the three coordinates. So it would be zero for a reason 0 to uh, x, so 0 to L in x axis, and 0 to L in y axis, and also 0 to uh, L in z axis as well. So it would be a cubicle in all these three in all this three reason, meaning the you have a cubical region inside. So inside that cubical region, your potential is essentially zero. But if you have a rectangular type system, so instead of it would be 0 to L, it could be 0 to twice of L. It could be 0 to some L prime, some like could be L by 2 or something. So then this would become your rectangular well. But in one dimensional, it is not necessary to like specify whether it's square or rectangular. So I hope that is what you mean. So like, is that what you wanted to know, like cubical well, or so like somebody was having that question. So Gokula Priyan. So did you get the point, or hello? Are you here? Okay, yeah, thanks. Okay, so any more questions? Okay, so yeah, so for one dimensional well, so you have just a one dimensional region of 0 to L. So as specified in this question right here, where you will find the potential to be 0. So let's so we have drawn this x-axis, and let's draw the like y-axis over here. So 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 in your um, so this represents your potential, so your y-axis. So and yeah, so within this region you have from 0 to L. So from 0 to L, you have your potential to be 0, and from like rest onwards, you have something very infinite, something very large value of potential. So here you have absolutely uh, 0. So here v of x is 0. Okay. So now you have some particle of mass m. Can't see the question properly. So yeah, like I just read out the question like just for like one time. I just said I'm basically explaining the question right here. So in this picture, so I'm saying that there is a one-dimensional well. So okay, yeah. So I'm saying there is a one-dimensional well. So where this one-dimensional well is given by this some potential v of x varying over x. So in x-axis you will find in this one-dimensional region there is a one sub-region that is from 0 to L, where you will find the potential to be absolutely zero, and in other places you have uh, I mean your potential to be something infinite. So here you have infinite potential, and so do here. So and your particle is trapped inside this zero potential region. So this is of some mass m. So now, uh, next, it is said that that trapped that particle which is inside this zero potential region of this one-dimensional infinite well, have a wave function that is given by this, and zero outside. Yeah, so it is completely the particle is trapped inside this well. So the particle it doesn't have any wave function outside this boundary region, outside this like uh, this 0 to L region. So you will find, if the particle is right here, you will find some wave function associated with it over here in this 0 to L region. So, and that is given to be this. So uh, then if that is so, then calculate the expectation value of the energy of the particle. So okay, uh, so now how to move on with this. So so from your, if you recall from your quantum mechanics like one course, you'll find that like you solve this type of system first, starting with your Schrodinger equation, and you will find that if you solve the Schrodinger equation, the solutions of that Schrodinger equation will basically give you the um, I hope like you are um, I mean, if you remember, like you write the Schrodinger equation, something of this plus 2m over x bar square, like e, uh, right? So if you use the Schrodinger equation, so so here we are talking about time independent system. So this is time independent Schrodinger equation. So so the solutions basically gives you the energy eigenstates of this infinite potential well for the particle trapped inside this zero potential region. So so the solution, so this is something like which is like elaborately given in like many textbooks. So this is just quantum mechanics one like a concept, so you can find it like everywhere. So I'm directly going to the solution, because that is what we will be using here to calculate the expectation value, and this is something which is quite standard. It's better you can also try to remember it. It's not difficult to like remember. So you can find that like the this wave functions, like the solution or let me just slightly add this notations to be something this. So your phi is basically your wave functions. So your if you solve this, so you will get I this I mean your wave function to be dependent on some integer, this n, and that makes, you will find that this to be something the solutions corresponding to energy eigenstates. So you will find some normalization constant, and then you will have sinusoidal sine n pi over L x. So this is basically the solution for for the particle trapped inside the region 0 to L, and it is 0 otherwise. Yeah. So this is if the particle is in ground state, you will have n equals to 1 uh, here. So uh, your wave function or the eigen wave function would simply be a sine pi x over L, and 2 you will have the first excited state, and so on. It goes from 1 onwards. So this n is your principal quantum number here in this case. So but in the question you will find it is already given that like the particle inside this infinite well has already it is already in some initial state which is given by psi x, and that is a sine cube pi x over L. And you see that like it is not any ground state or first excited state, because this, you will see that it is sine of cube. So uh, but from the solutions of Schrodinger equation for the infinite well potential, you just have some sine n pi over Lx. So even if you put n equals to 1, so it is still sine pi x over L. So it is not you will not find the solutions to be sine cube. It is so it is linear. Uh, so if it is given in sine cube, it means that you can break that sine cube expression into linear powers, which then it would take the form of linear superposition. So it is basically the initial state which is given right here. It is in some superposition state. So, for example, if you just recall, again, just one basic trigonometry identity. So if you remember, like sine of uh, 3 uh, 3x, or yeah, whatever, sorry, sine of 3 alpha, you have something 3 sine alpha and minus 4 sine cube alpha, uh, right? So so then sine cube alpha, I can write it as 3 over sine alpha minus 1 over 4 sine 3 alpha. So here you can see that, like, I can write this um, simply as linear powers of sine alpha. So similarly, in the question which is it is said that initial state of the given particle is in some sine cube pi x over L, I can write it as some linear powers of a sinusoidal function. So that will give me uh, so if I so, uh, so the initial state of the particle inside the potential well is psi of x, which is given to be a sine cube pi x over L. So this you can write it as 3a over 4 sine uh, pi x over L, then a by 4 sine 3 pi x over L. So now you find uh, yeah. Okay, so yeah, so this is the initial state you have now. You have the initial state. With this state, you have to find out the expectation value with which this particle is like I mean with which this particle is inside the infinite well. So like, to calculate expectation value, like for any expectation value, whether it is momentum, energy, or some other physical observable, so you need the information about the state of the particle. So the state of the particle was given in your question to be this. So on expansion, you find out this, and this expansion is necessary because you know the uh, uh, I mean, you know the wave function of infinite well in terms of eigenstates if you solve the Schrodinger equation, which is which would come out to be this. So, and also corresponding to it, you know the energy eigenstate. So these are, if I say you also okay, let me. So these are uh, uh, these are energy eigenwave function, eigenwave function, and also you have uh, energy eigenvalue. So which will be it is something given as n square pi square h bar square over 2m l square. So yeah, so this is a energy eigenvalue for your infinite one. So this all you will basically you can deduce them like once you solve the Schrodinger equation. So okay, so we will be exploiting these two things to solve your expectation value or the average value of energy. So that is what your final point of the question. So final point of your problem. So you yeah, so now we can find out. So as I said, to find out any expectation or average value, you need the information of the wave function, you need the information of the state of that particle for which you will calculate its average value or the expectation value. So and before that, just one more thing. So now suppose if you have some wave function, let's say psi of x, something, let's say c1 phi 1 x plus c2 uh, yeah, c2 phi 2 x plus so on to cn phi n x. So if this is so, you will find that the yeah, so here uh, phi 1 phi 2 and phi n are your eigenstates, and C1, C2, and Cn are your transition coefficients, or basically this is something transition amplitudes. Or if you take the uh, magnitude square of this values c1 square, so this can be in general complex numbers. So c1 magnitude square, c2 magnitude square, and so on. If you uh, take this magnitude square of this complex numbers, like you basically find out the probabilities, you basically find out the probability of uh, particle going to nth uh, eigenstate or or eigenwave function. Basically, it means it is what is the probability that it will attain this nth eigenwave function from whatever its initial wave function was. So the initial wave function here we know well, exactly very well in the question which is given. So this is our initial wave function, this thing. So yeah, right. So if I'm telling you all this because this is very standard to speak here. So let me complete it first. So this thing I'm okay. So here, if this is the thing like given to you, or this is the thing that you know it beforehand, then what you can do, like if you want to know the expectation value of the energy, so or maybe I can quickly just say, so the expectation value of energy will be something given as psi x um, h of psi x. So Maybe like I can quickly tell you one thing right here. See this 5152 and all this expression which I have written here, I can simply just write them down in Dirac notation. Like instead of 51, I can write it as 51 ket. So these are the same thing, but written down in different representation. One is in if I write in terms of functions like this, so it would be the Schrodinger representation. In Dirac, you can just simply write it in algebraic way. 51. Uh, was there some question? Like, does anybody want to speak? Okay. So yeah, the same I can write it as to be phi two. So this is all in Dirac notation. Dirac. So again, this is something you have probably seen in your quantum mechanics one course as well. So and this becomes quite easy to solve your algebra related to the any type of computation that you do in quantum mechanics. So if you try to solve using this complete wave functions in terms of polynomial or whatever functions that you see here, so you have to integrate out and you have to evaluate the overlap integrals and all of those things. So instead going that way, we can just simply say so, or I can just simply write the wave function once again. If psi is your uh, some linear superposition wave function, I can write it to be phi 1 phi 2 cn phi n, right? Then yeah, so uh, right, yeah. So if psi is given to be this, then this is ket psi, and then bra psi is basically the complex conjugate of this ket psi. So the complex conjugate of ket psi is this. So you have to take the dagger. So you have to basically take the complex conjugation. So then that will give you C1 star uh, bra phi 1 plus C2 star bra phi 2 plus this goes on till Cn star bra phi n, and this is you have to yeah. So on left you have this complex conjugate of psi, and so in the middle you have the Hamiltonian operator, and this will operate on your right on psi. So this will be C1 phi 1 plus C2 phi 2, then till Cn phi n. So if you evaluate this, you will find that so and these are remember all these are your eigenstates, and by eigenstates we mean that if you have some phi m phi n inner product, so this is basically um, so if you have some inner product, then you have direct delta, you have delta function basically. So it would be if let's say if phi m and phi n are normalized, are normalized eigenfunctions or eigenstates. uh, okay, then yeah, so in or otherwise you can write it as in terms of integral, it would be phi m star x phi n So this is this one in Dirac notation, and normally in Schrodinger way we can it would something written like this. Uh, yeah. So so this means like if m and n are equal, then you will have the overlap integral or the inner product to be one. If they are m and n are not equal, which means they are orthogonal states, orthogonal wave functions. Which means you have zero inner product value or zero overlap integral value. So using that information, suppose if I start, let's first operate this h on your right, so which is in the parenthesis. So when h will act on phi 1, so this is phi 1, it will give you e1 phi 1. So because since these are the eigen wave functions of sorry, so phi n's are eigen states of h. So this means if I act h on phi 1, it will give e1 phi 1 and so on. Like it will go like this. So I will have c1 star phi 1 uh, plus c2 star phi 2 cn star phi n, and this uh, uh, just 1 second. Okay. Yeah, I'm just creating some space here. So yeah, fine. So on the right, so after you operate h on phi 1 phi 2 uh, rest of the terms, so you will find out it would be something c1 e1 phi 1 plus c2 e2 phi 2, and yeah, it will go till the last term, and then you will find the uh, yeah, you will find uh, following: c1 uh, magnitude square times e1 plus c2 magnitude square times e2 plus cn magnitude square en. Then this is basically in a concise way you can write it as summation over n for all magnitude square of cn multiplied with its corresponding en value, the energy eigenvalue. So this is your expectation value. So this is very quite standard way uh, to write if you are trying to calculate the expectation value of any physical observable, which is in uh, what which is in some linear combination. Then you can write it this way. So you can use directly the final form right here, and um, using this I can calculate the expectation value finally for the given question. So uh, so uh, so instead yeah, so if you see our initial wave function uh, was this. So this was your initial wave function. So let me just okay. mm, so this psi x is our initial wave function. So I can write this psi as 3a over 4. So sine pi x over L. So if you see, this is our phi 1, and then you have minus a over 4 and sine 3 pi x over L. So this is our uh, um, phi 3. So what are phi 1, phi 3? So like if you remember, as I said before, phi n is basically your nth energy eigenstate of your uh, um, of your infinite well. So this is, we have written initially the same thing I'm writing down here, sine n pi x over L. So with some normalization constant. So this is your uh, eigenstates for 1D infinite well. Okay, so then you have the initial state right here. So you can just simply calculate the uh, energy eigenvalues. From the prescription which just we studied right here. So which is basically, you take their corresponding coefficient values, and take their magnitude square and multiply with the eigenvalues. So here we have phi 1. So corresponding to phi 1, I have this c1. So which is, so this is c1. So if I take, yeah, so 3a by 4. So a is some real value, so it's a normalization constant. So 3a by 4, if I have to take the square, just normal square. So this is real value. And for phi 1, you have energy eigenvalue. So you have energy eigenvalue to be n square pi square s bar square by 2m l square. So this is energy eigenvalue for the 1D infinite well. For phi 1, you will have n equals to 1. So that is pi square h bar square, uh, pi square h bar square 2m l square. Then you have again plus minus a by 4 square. So that is, yeah, minus a by 4 square. Then phi 3 is basically 3 square pi square h bar square 2m l square. So yeah, so if you calculate this, you will find your energy eigenvalue. uh, yeah, so you basically just um, you just have to, this is 9 by 16 a square pi square h bar square. So it's basically 32 at the denominator over ml square plus this 9 again, uh, 9a square over 32 pi square h bar square ml square. So it's basically 18 over 32 a square pi square h bar square ml square. So this is what the expectation value. So yeah, uh, so is this clear, like, or you missed out somewhere, or you know like this very well, like how to compute this expectation value, or you have any issue or any problem? You can speak, you can unmute, you can anywhere at any point which you didn't found, or which you like didn't understand at all, like uh, you can speak.
Sir, how can you find this in three dimension?
Sorry, how can I?
Find this expectation value in three dimension. It would be same or we need to
In
find.
three dimension, you will have, instead of this, so in three dimension also, you, for any expectation value, you have to first find the state in which you have to compute the expectation. So like here we calculated the expectation value in some psi x. So there you will calculate the expectation in some three-dimensional initial state, which would be something psi x y z. So in that case, you will find that expectation value to be, let's say, again it is given to be two terms, like in this question also we had sine cube theta. So because of which we find two terms, two eigenstates were in linear superposition. So we had a linear superposition state initially, and using that linear superposition state, we calculated um, this energy expectation. So for three-dimensional case, you will have some, let's say, some linear superposition. If I'm taking it to be two, let's say C1, and the it has some phi one and C2 phi two, and this phi one would be in case of um, three-dimensional, it would be something like n pi x over yeah, just one second. Yeah, n pi x over L, then sine n pi y over L, then you will have sine uh, n pi z over L. So yeah, or if it is phi 2, sorry, so this n would be 1 if I'm taking it to be phi 1. So it depends, like and phi 2 would be there are also d's and races. So let's say I'm just writing it only one of the state. So sine it would be 2 pi x over L sine 2 pi y over L sine uh, yeah. So basically, like, I mean, it won't be only one quantum number. So in general it is given to be uh, n nlm. So it depends on three quantum number. Like in one dimension, as we so it depends only one quantum number phi n. So here, uh, in first case, I took it to be n equal to 1, L equal to 1, and m equal to 1. In the second case, so I should not write this to be phi 2. Instead, I can write it to be psi uh, psi 100, let's say, uh, and let's say this is psi 111. So in general it is given as phi nl. So, and in the question, let's say it is given to be phi 111 and phi uh, 100. So if this is the two states which are in linear superposition for a given initial state of the quantum particle, then these two would be your eigen functions. So, and this, instead of two which I have written down here, so it would be simply so yeah, sorry, like it cannot be zero here in harmonic potential. So either it would be 211. So 211. So two, this would be one, and so this would be your two states, two eigenstates of your three-dimensional cubic well, which is given to be your initial superposed wave function. So, and then you can do the same thing, like if so for this eigenwave function, you will have the energy, let's say, for this eigenfunction you will have energy eigenvalue to be uh, 1 square plus 1 square plus 1 square pi square h bar square over 2m L square. So in general, it is given to be E and Lm is n square nx, yeah, n square plus L square plus m square uh, pi square h bar square over 2 ml square. So yeah, so then yeah, so this would be your energy eigenvalue for the first eigenstate for this eigenstate. So you have this the expression right here, and the energy eigenvalue is this. So you have the energy eigenvalue for the first eigenstate, so and you have c1, and similarly you can calculate the energy eigenvalue, or you can write the energy eigenvalue of phi 2 1 1 state, and you also have c2, and with this you can again use this relation, and you can calculate the energy eigenvalue, which is for your three-dimensional infinite wave. So did you get the point? Or like, so you have to use three-dimensional eigenwave function and three-dimensional energy eigenvalue. So if you want to calculate the same expectation value of the Hamiltonian in for a three-dimensional infinite, so that is what you need to do. Did you get? Uh,
Yes, sir.
okay. So, any other questions or anything which not clear? Uh, yeah, you can speak like anything which you could not able to understand here. Uh, like any silly thing, or even the simplest thing is fine. Like this is all basic thing we need to first remember the basic thing first, so then we can go to more like advanced stuff as we move on to the next topics of quantum mechanics. And of course you are doing advanced quantum mechanics course, so these are some basic things which you can clear right here at the moment, because as you go on to um, through the uh, succeeding topics, you will find these things would be like I mean these things would will just simply surpass, and you would be exploiting them like without like you would be using them so much like I mean you would find it would be very difficult to come back and see like what you have missed or what you have not remembered. So
Hello, sir.
is there some other question? Yeah. Was there any question?
Sir, I was late for this class. Could you
Okay.
repeat what question are you telling?
Oh, okay. So yeah, like I was just like today we were doing some like like the basic problems of quantum mechanics is basically the quantum mechanics level one problems, like or quantum like the problems that you find normally on quantum mechanics level one topics. So here we were solving one of the simplest quantum mechanical system, that is 1D infinite well. So we were trying to calculate the expectation value for the particle inside the one dimensional infinite well, which where the initial state was something given to be this. So and in this so this is something, if you expand this, you will find that this is in some linear superposition state, so linear combination of eigenstates of the 1D infinite well. So where we have uh, written it down like here. So then we understand how to calculate the expectation value for linear superposition states for any quantum system. So here you can use a very concise expression to calculate the expectation value. So you can check the entire thing like maybe once we are done with this live session, you will get a recorded session where you can follow step by step how we have trying to calculate this expectation value. So it's I mean it's not very difficult, so you can follow, like if there is something still missing, like you can try to ask. So uh, in a nutshell, what I'm trying to say, like we were just trying to calculate some energy eigenvalue of a quantum system which was initially in some linear superposed state for a one dimensional infinite well. So uh, So maybe you can like we just discussed it maybe quite thoroughly, so maybe it won't be difficult to check back the entire discussion that we just did. So you can do that once, and if you are still having some issue, you can surely you can drop here and like ask your problem. So we were just trying to calculate the expectation value. So
Yes, thank you so much for that.
yeah.
I would see record lecture.
Yeah, sure. Yeah, you can access it in through your portal. So yeah, so you won't maybe you won't get it immediately today. Maybe by tomorrow, or maybe within 2 3 days, you will get the recorded session and the working notes also, which we are discussing right here. So that also will be shared with you. So yeah,
Okay, okay.
yeah, okay. Okay, if there's any other question, like we can quickly go on, or maybe we can go with the next question and we can come back if there is any other question. Um, okay, so if there's no more questions, so we can um, go to the next problem. So it's again on this infinite well. So here uh, the particle is again inside this infinite well. So this time it is not from 0 to L, so it is from minus L by 2 to L by 2. So this is a bit different from the previous infinite well. So the previous infinite well was trapped between 0 to L. So if you have minus L by 2 to L by 2, it's like a you will find the wave functions to be symmetric. So yeah, and initially you again have some linear superposition state, so which is again a combination of phi 1 and phi 3, so similar to what we have seen previously also. So now phi 1 and phi 3 are normalized ground and the second excited state. Calculate the following. So let me fill it. uh, so first uh, you need to calculate this shortest time t after which the state will repeat itself. Okay, so what it means basically, so you have a initial state psi uh, x t equals to 0. So this is your at t equals to 0, which is given in your problem, that it was something of linear superposition of phi 1 and phi 3. So so what is given here? So so you have this initial state, and if you let this quantum system as it is, so in time you will find that this system will evolve, and you will find that at some times psi x t prime or t equals to t prime, you will find that this system will be um, yeah. So at t equals to t prime, so this will be no more psi x. So this is not going to be psi x t equals to 0. So it will change. It will change to something else. So it could be a linear combination of like half phi 1, and then could be something half yeah, root 3 uh, phi 4, or it could be also something, let's say something uh, phi yeah, it could be something five as well. So there could be many other terms, or it would be definitely something else which won't be the initial state. But again, at some uh, uh, time, let's say that time to be uh, t equals to t double prime, so it will become exactly the same as psi x t equals to 0. So uh, let me call that to be t0, let's say t0. Yeah, so we'll have some t0 time which will be exactly this. So what will be the time that we have to find? We have to basically find out what is t0. Yeah, uh, this t0 we have to find out. So like how to do this? So there is the time evolution which you need to understand how you can time evolve your quantum state. So the initial quantum state is given to be this is your initial quantum state. So uh, now whenever you have like so to in order to evolve a quantum state, so what you do basically, uh, and uh, if your Hamiltonian if you're Hamiltonian is time independent. So all this which we are trying to see here, this is for time independent states. So this would get little complicated if we have time dependent states. So if we have time dependent system, instead we have time independent Hamiltonian, it becomes a bit easier to work on certain things. But for time dependent things, surely you will find um, more. I mean. Effective ways to deal with it in your advanced quantum mechanics course, which is we are doing right now. Maybe in the upcoming topics you will see how to smartly deal with time dependent Hamiltonian systems. So for time independent, it's not that difficult right here. So suppose if you have uh, phi and is some uh, initial uh, eigenstate, then I can write the uh, is some initial eigenstate. So this means phi and t equals to 0. So this is phi and t equals to 0. So if I want to know phi and t equals to t, then uh, you have to operate something called evolution operator, which is phi and t equals to 0. So this is something, yeah, like you can find out like from Schrodinger equation itself. Like you can write from time evolution equation, basically you get this to be of the following form. So ht phi n, so this is your Hamiltonian, uh, t equals to 0. So when this is your basically your operator, evolution operator. So this will act on the eigenstate on the right. So once it acts on the eigenstate on the right, so you will find when h will act on phi n, so it will give you en. So that is what the eigenstate does whenever the operator acts on it. So you will get its corresponding eigenvalue. So it will be phi n t equals to 0. So yeah. So for any eigenstate, you will find its uh, time evolution would be something given of this following form. So again, we will be using this uh, in our uh, advantage to find out the evolution of the initial state which is given to us. So and if suppose if the uh, so if the initial state it's not just purely phi n. If it would be uh, linear combination of this phi n, like if it would be um, like what? Okay, we can do that. So already in our question it is given to be linear combination of phi, so you can directly see here. So uh, right, so now we can go to our case where psi is given to be some initial state, and we have to evolve it. So then uh, psi uh, x t equal to, let's say we want to find out that time we want to find out uh, okay, let's, yeah, so we want to evolve it to some time t prime. So then uh, we have to use the evolution operator, as I said. So this is again some, yeah, so this is basically your key strategy how to evolve a state. So the same thing we will do, but this time this is given to a linear combination state, so we will act a evolution operator on the initial state. So the initial state is given to be psi x t equals to 0, so which is in some linear combination. So if you see, it is given to be 1 half of phi 1 and I root 3 half of phi 3. So 1 half of phi 1 plus I root 3 over 2 uh, of phi 3, right? And now so the evolution operator, as we wrote it right here, so this is given to be this, and this evolution operator will act on your half phi 1 plus, so first this will act on this, and then this will act on the second term. So first, when it will act on the first term, it will give you exponential I h bar. uh, so this is, there will be a minus sign, yeah. So on the first, so when it will act on the first term, so and remember, this is, we are trying to calculate at t equals to t prime. So at t equals to t prime, this means this will be u of t prime, this t prime. So yeah, e1 t prime, then half of, so let me write down the half factor outside, half of phi 1, yeah. So the when the first, so when this evolution operator acts on the phi 1, so this is what you will get on, and when it will act on the second term, so you will get exponential, uh, right, minus I over h bar e3 t prime phi 3, right? So let me create some space. So yeah, this is what you will get after evolving some time, after evolving it to some uh, t prime time. So you have some initial state, you have some initial quantum state, and you evolved it to some t equal to t prime. So you had that state, you had that quantum state at t equals to 0, and we have evolved that state to t equal to t prime, which would look like this. So and now, but the question is, there is a there exists a time. So there you will find a time, so which is basically t0, where basically this at t0, the evolved state will become equal to the initial state. So it's basically, some quantum state, it is basically oscillating uh, to various states. So that means if it is the wave function which is evolving in time and it is oscillatory in nature, then it is sure that it can retain its um, uh, initial state at some point of time in its time evolution. So so now, like, our goal is to check or basically to find that now psi x t equals to t naught, the state basically becomes equal, basically becomes similar to t equals to 0 state. So that means so psi x t equals to t naught. So so uh, let me just change everything whatever I have written t prime. So write t prime equal to t naught. uh, it will be just half, yeah, if you e1 t naught phi 1 plus I root 3 t naught phi 3. So now what I can do, I can take a overall common factor. So what is that common factor? I can take an overall common factor of uh, minus I over h bar e1, uh, half of phi 1 plus I root 3 by over 2 exponential uh, minus I over h bar, or I can write this minus I e3 minus e1, e3 minus e1 over h bar t naught phi 3. So this is, I have not done anything I mean, uh, yeah, this is not something, I have not suddenly made anything serious here. So it is just simply I have took a common factor of exponential, this thing, the first exponential factor, I have taken it to be a common factor from both the terms. So then you will find the first term without that exponential factor because I have taken that to be a common factor. And then you can just, if I'm taking this as a common factor, then you will just divide it with this exponential. Then you will find the overall exponential on the second term to be this. So this is just taking a overall common factor. And why is it so? Because this common factor now, we can just ignore it. We can ignore uh, this overall uh, common factor, as it will not change the physical information. By that, it basically means, suppose if I have some, let's say, uh, I mean, it basically means, let's say, if I have some state psi uh, psi xt, and if I am multiplying with some, let's say, some phase I like phi, some phase I am multiplying, let's say ei theta, I am making this state to be I'm basically like changing the phase of this quantum state. If I do so, you will find, if like when the state was in uh, like initially when the state was without this overall phase, its probability was something psi xt square, and now it it will again, if you will find the probability, so these are probability. So again here also I will find the probability to be again psi xt square. So this means like I'm not changing any physical outcome by introducing an extra overall phase factor. So the same thing here also, if I have this, if this is my total state, then if I multiply a overall phase factor, then I am not changing uh, any physical information or any probability outcome. So I can ignore it or I can keep this phase. So it will not matter much when it comes to uh, the probability value. So because that is what after all we need, like even when we are trying to solve any average values, or when we are trying to calculate any probability values. So that is what the physical uh, um, deduction that we do when we are trying to solve any quantities in quantum mechanics. So yeah, so now I can just simply like forget about that overall factor, and then my state will just basically become psi x t equals to uh, t naught, which we are looking at. So it will become half of phi 1 plus square root 3 over 2 exponential minus I e3 minus e1 over h bar uh, t naught phi 3. So right. So then as I was so yeah, so in the question as it is given that this has to be equal to the so this, so this is equal to the initial state. So now we can just simply put it equal to the initial state. So this is equal to uh, so the initial state, if you see, the initial state was given to be half of phi 1 plus square root 3 2 uh, I square root 3 2 phi 3. So this is something, uh, so there is one I have missed here. So this is what the initial state uh, in the question here itself given. So now if this is equal to the state after time t naught, then comparing both side of equation. So if we compare both side of the expression, so where psi x t equal to t naught is this, and where psi x t equals to 0 is this, then we can uh, write it down. So this implies exponential of, so basically the two sides of the equation differs by only this factor right here on the second term. So so I have exponential minus I e3 minus e1 over h bar t naught equals to 1. So now so if you remember, I can so exponential of anything iota is basically something of oscillatory type expression, or something I can write it as uh, um, like if you remember from Euler's relation, so I can write exponential of I theta as something cos theta plus I sine theta. And so if I, so in general I can also write exponential of minus I 2 m pi equals to 1. Like this is something quite general, because if you write cos of 2 m pi and cos of 2 m pi, then plus I of sine 2 pi is basically 0, then this is basically you get 1. So that is why it is generally you can write exponential of minus I 2 m pi is always going to be 1. So right. So from here, so this implies that, so where m can be 0, 1, 2, anything. So this means exponential of minus I e3 minus e1 over h bar t naught equals to exponential of minus I 2m pi. Now this implies e3 minus e1 over h bar t t naught equals to 2m pi. So this implies t naught equals to 2m pi over h bar over e3 minus e1. So this means your after uh, so if t naught equals to 0, so that means your initial state itself. And if so your, as I said, uh, m can be 0, 1, 2, 3. So if I put m equals to 0, that t naught is basically 0. And if I put m equals to 1, then your t naught is will be 2 pi h bar over e3 minus e1, which means after 2 pi h bar e3 minus e1, you will get the state which is exactly equal to the initial state. And again, after another interval, which is if I put m equals to 2, you will get 4 pi h bar e3 minus e1. You will again get the state which would be exactly equal to the initial state, and this keeps on repeating. So because the state which is evolving in time, it is in some oscillatory behavior, it is in some periodic behaviors, uh, which it will keep repeating its initial state again and again in time. So the time which we were supposed to ask, the which were asked in the question, is basically we have to find out what are these times. So this is the time which we needed to show. So so yeah, that was about that problem. So again, so any questions on this or anything not clear here, so please, uh, you can speak now. You can uh, tell me exactly what was not clear or any problem.
So they asked about shortest time.
uh, yeah, the shortest time, if it is asked about the shortest time, then you will take, because t naught equals to 0 is itself is your initial time, the initial moment uh, of your wave function, initial instant of your time, initial instant where the state was prepared, then uh, so this is m equals to 0 is a very trivial case. So for m equal to 1 is your shortest time, so this corresponds to t naught 2 pi h bar e3 minus e1. So this is your shortest time. So this is what you mean. So the shortest time, if it is exactly what you mean shortest time, then it should be 2 pi h bar over e3 minus e1. So right, this is what you wanted to know, right? uh, Hello. uh,
Yes, sorry.
yeah,
Next.
yeah. So yeah, any other question, anything? uh, you can speak, like anything not clear anywhere throughout, yeah, or even in the previous
Sir,
question. Yeah,
sir, why there is we write 2m pi
yeah, yeah,
the
yeah.
equation e3 minus e1 by h bar.
Right.
We,
So you mean like, uh, uh, yeah, so you mean basically, why do we write this one to be this?
yeah, yes.
Yeah. So why I can write this, because if you see on the left hand side, I have some uh, this is what this is something, Euler's function. So this is something exponential of I theta, right? So this is some uh, exponential of I theta, it means something of oscillatory nature, something you can express it down in terms of sine and cosine. So so if it is equal to 1, so it is so from your like what, from your mathematical methods uh, knowledge, you can find out. So any uh, so any Euler's function of this form, exponential of ei theta, uh, is written it down in terms of cos theta plus I sine theta. So if this is the definition, so if ei theta equal to cos theta plus I sine theta, then this means for every exponential of minus I 2m pi, so if theta equals to 2m pi, then this will always give you 1. So whatever value of m. So that is why, because we know this exponential of I theta uh, is written down in terms of cos theta plus I sine theta, then we can write down exponential of minus I 2m pi will always give me 1. So so that is why, uh, uh, so so you check this. If I again expand it in terms of this definition, so let's say if I
Yes, I
again,
understand.
yeah, you got it right. So if I again expand it in terms of cos of 2m pi plus I of sine 2m pi, then this will basically give me 1. So that is why. So this is just like simple mathematical like relation between the Euler relation. Yeah, this is just yeah, simple mathematical identity. uh, for final written exam, what should we follow? Could you just like specify a bit more? Like I didn't get like uh, which book should we follow, or you suggest for this type? Okay, so problems like, yeah, there are basically there are advanced topics. There are like, if you, it won't be exactly like one particular book you can follow to get all type, to cover all the topics. So like from some books like which is one, like everyone's favorite is like Griffith's Introduction to Quantum Mechanics. This is something which you can always keep on practicing. But for more advanced topics, you can go to Sakurai, you can go to like Cohen Tanursi. So this would be like little there would be, it would be covering some more standard problems, but it would be very essential to understand them. Like it would be like essential to get the ideas of the concept that is involved here. And also Jet Li is one of the like nice books. Like you can also get some nice problems there. So so I cannot guarantee you like to to get a book and find problems for all the relevant topics that you will see here. So for here, if you see all the problems that will be done in the assignments in this course throughout from week 1 to week 8, and also the topics or problems that we will be discussing in live sessions. So that itself will help you to cover most of the things. So that would be like that would be like more than enough to understand the important concepts, and also that will cover important problems. So which I think uh, I mean, there could be some one or two topics like which, because even if we are doing 8 week of uh, course, there will involve a lot of multiple topics. But to cover questions from each of them, it would be difficult. So some like one or two topics we can miss out, or maybe like for the sake of time, like we could not complete it. So some problems could be missed. So you can happily come back and ask for that problem related to that topic, which might be we are missing. So but we can always report it, so that we can try to find out a problem for that topic and try to do. But for your exam related thing, like you can always follow whatever topics that will be covered here. So it would be more or less going to be exactly those kind of problems. So it won't be any extraordinarily, not going to be very different type of problem you would be asked in your exam from whatever we are going to do here. So Yeah. So, but for your practice, there are many good books you can always try to see, as I named a few of them. So, and there are also lecture notes which you can always find more interesting problems also. So, Uh, yeah, so this is basically our first live session. So you have not missed any live session before. So probably like, yeah, there was supposed to be, yeah, this is something like might have confused most of you, because the live session was supposed to be on last week, but it was cancelled for some reason, and we are doing this live session. This is our first live session. So here. This evening, and yeah, we will be doing our next live session again tomorrow. So yeah, this is our first live session. Yeah, yeah, okay, thanks, Arup. So yeah, any other question, anything uh, you wanted to ask, or anything not cleared here, you can speak. Okay, if you are not having any other question, then you can see one more problem here. So this is related to your harmonic oscillator problem. So, or let me just quickly. Okay, maybe there is one more following question to it. Maybe I can just quickly give you some hints to it, and we can move on to the next one. So the next thing was uh, find the so first we find out the shortest time, then the yeah, calculate the following, the shortest time, then calculate the uh, this calculate the uncertainty uh, in the energy of the particle in the given state, of the particle in the given state. So uncertainty in energy, it basically means you have to calculate this statistical deviation. So a statistical deviation, like from even from your mathematics, which you know. So this is basically the difference of uh, expectation value of the square of energy and the square of expectation value of energy. So we understood how to calculate the expectation value of energy. So as we just discussed very in length about how to calculate the expectation of energy of a Hamiltonian, for which the initial state to be given to be some linear superposition, then you have to take the summation of the Cn square, then multiply with its corresponding energy eigenvalue. Same way, if you want to calculate the expectation value of energy square, then you have to do the same thing, but now you have to multiply it with the square of the energy eigenvalue, and then and doing that, like so yeah, so you calculate the uh, energy which is uh, expectation of energy first. So for that, like again, if you remember, we had the initial state was given to be uh, two was composed of two states. So this is phi 1 and phi 3. So these are your C1 and C2 or C3, and then multiply with their corresponding energy eigenvalues. So yeah, I think you can do the same strategy which we did last time. So from here on, it follows the same thing which we did last time around. So maybe I can just yeah. So this will be less C1 square E1 plus C3 square E3, and again you can calculate E square average, which will be C1 square E1 square plus C3 square E3 square. And then yeah, then you calculate what is delta E upon using these two values of uh, E square and uh, expectation of E square. Sorry, expectation of E squares. I mean square of expectation of E. So right. So this is uncertainty in E. So yeah. So this is just straightforward as we discussed before. Yeah. So any doubt here you can speak. I'm just skipping it. This is something we just what we just exactly did in the first question. Yeah, if there is any question you can ask, like anything not clear.
So
Yeah, yeah.
in all other states, we write like ground state and first accelerated state. Is it always like that, or it can be like two ground states and
No, no.
state
Here we
accelerated?
have initial state. One is ground state, and the second was the second excited state. So if you see, so our initial state was phi 1 and phi 3. So phi 1, so for infinite well, n equals to 1 is your ground state. So this is your ground state, and n equals to 2 is your first excited state, excited state, and n equals to 3 is your second excited state. So it can be any linear combination. It can be linear combination of two of them, three of them, or can be n of them. Could be like 100 of them, or it can be just a pair of them. So it doesn't matter. So and it can be any. You can take any permutation. So there is no problem with that. So there is no any restriction for a superposition of any I mean you want to get a superposition state, so you can combine any states you want.
So I'm asking that let's say we have a state vector psi 2. Can we take it as a ground state and other excited state as psi 3, psi 4, something like that?
Sorry, I'm not still with you. So if you want to, could you just repeat one
Uh,
more time?
Sir, let's say I have a state vector psi 2. Can I take it as a ground state
uh,
and make other states psi 3, psi 4 as excited state?
you are telling you want to prepare another state side 2, uh, which is basically your ground state.
Yeah.
Yeah.
Can we make it like that?
Yeah, you want to have a another state which is your ground state. Okay, so then the question is like you want to calculate the expectation value inside to the you want that. I mean, you can prepare any state. Like you can prepare a state which only has only one eigenstate also, but that won't be a linear superposition state. So you can take another state psi 3, which would be again something just a linear which would be again another some eigenstate. So so sorry, maybe I'm not still following your question. Like is it what you wanted to know or something else?
No, I'm asking can we assign the ground state for
uh,
any other state vectors? That's what I'm saying. Even if it is the superposition, we
uh,
only like assign a psi 1 as a ground state, not psi 2 or psi 3.
You mean this phi one, the phi one which we are denoting
Sorry,
here?
5 1. Yeah,
Yeah.
yeah, yeah. Yes, yes.
Okay, you are telling phi one we are taking it to be ground state. Why we cannot take phi two, phi three to be the ground states? Is that your
Yeah,
question?
yes, sir. Yes, sir.
Oh, okay.
Okay.
So yeah, phi one. Why you call this as your ground state? Because if you if you see these are the eigenstates of what? So these are the eigenstates of your Hamiltonian. So Hamiltonian or the energy of your system, so physical observable energy that what we are trying to analyze here. So if you see the if you get when you solve Schrodinger equation, you get these are the eigen wave function or eigenstate. You will get phi one, phi two, phi three, phi four, whatever. Uh, you will get all the possible values of n. So now then correspondingly you will get also eigenvalues to them. So when you try to solve this linear system of equations, you get the eigenvectors and corresponding eigenvalues. Now what we do, what we call ground state here are basically in this case we have one boundary, meaning we have the n starts from 1 and it goes to till infinite. So it has many. You can go to any value of n, any higher value of n. So if you compare all the values from n equal to 1 to n equal to 2 to so on to any higher values of n, if you compare all the corresponding energy eigenvalues, you will find that there exists a one value which is n equal to 1, correspondingly which you have E1, which has the lowest value. So corresponding to that lowest value, whatever its eigenfunction, so the eigenfunction is phi one. You call that is to be a ground state, or you call that to be a lowest weighted state. So in more technical way, you can say the lowest weighted state. Or if you had something like only four states, like from like for example, you had phi one, phi two, phi three. So if you had phi one, phi two, phi three, if this is your case, then and you cannot have any higher values than n3. So n greater than 3 is not allowed. So it's, and also n less than 1 is not allowed. Then you will find some values e1, e2, e3. So in that case, you will find that E1 could be your the lowest value, E2 could be your second lowest, and E3 could be your highest. So then in that case, you can say this is your ground state or your lowest weighted state, and this is your highest weighted state. So this way we say like highest weighted value, which means this correspond to highest weighted state phi 3, and this corresponds to lowest weighted state phi 1, and that is what we call here as ground state. So if E2 is not your lowest weight value, then you cannot say that to be your ground state or something. Maybe there are some uh, other approaches like what we do, like and this is something you can make some kind of a what uh, orthogonal transformations or some rotation or some kind of unitary transformation where you can rotate the states basically in the Hilbert space. In that scenario you can change like phi 1 to phi 2 and phi 3 to mix up into one another. And in that scenario then you can find a new state where you will find phi 1 is not your ground state, maybe some phi 1 prime could be your ground state. And that will happen when you do some unitary transformation. Maybe you can see one kind of that unitary transformation in one of your upcoming topics. But for now, like what we are having, you cannot say phi 2 phi 3 to be your ground state unless you make any kind of unitary transformation, and then you say so. But how we are calling it as ground state, this is the way we are looking into its energy eigenvalues, and then we are saying this is the lowest energy eigenvalue we are having. So if E2 is the lowest energy eigenvalue, then corresponding state E2 can be your ground state. If it is not, then E1 will be your lowest energy eigenvalue, and corresponding state it's your ground state. So that is what
Yes, sir. Right. Got it.
you got the point, right?
Yes.
Okay, okay, yeah, thanks. Okay, so any other doubts?
Sir,
Anything? Yeah,
hello.
yeah.
Sir, you regarding three-dimensional case, you told me no
Uh-huh.
that when Hamiltonian act on a psi,
Uh-huh.
it will have a degeneracy there. Does it
Yeah,
mean
yeah, yeah.
we will get a set of eigenvalues, not a one eigenvalue?
No, no. Degeneracy means you will have the same eigenvalue for two to three different distinct eigenstates. So, for example,
Okay.
like as I was talking about one of the three-dimensional eigenstate. So here in this case,
Yes, sir.
so
Yes, sir.
yeah, so in this case, you will find 5211 is a eigenstep, and also you will find 5121 is also one eigenstep, and also you will find 5112 is also eigenstep, and
Uh, the, due,
all the three will have the same eigenvalue.
due to this combination, sir,
Uh,
this element combination.
Yeah, yeah, NLM. So you basically permute NLM. So you
Uh,
first increase N. So NLM will start from 111 because it
yes,
cannot
yes,
be starting from 0. So all of them will
yes, sir.
start from 1 1. So that will be your ground state. If you calculate the corresponding eigenvalue, it will be the lowest value. And then you
That's
can
why.
increase either N1 first, or you can increase L or M. So either of three you increase to one value. So if you increase, let's say n, then you will get 211, and then instead of increasing n from 1 to 2, you can increase l to 1 to 2. So that will be 1 to 1. So this one, and
Okay.
then you can increase the, or you can increase the last m quantum number from 1 to 2, it will be 112. So but you will find all the three will have the same eigenvalue. So they will have, if you see, it will 2 square plus 1 square plus 1 square pi square h bar square over 2ml square, or it would be either 1 square 2 square plus 1 square, or it would be 1 square plus 1 square plus 2 square. All of the three are basically the same values. So that is why, so
Yes.
you have three distinct states having same eigenvalue. So that is why they are the degenerate states.
Three distinct state having
Same
same
eigenvalue,
eigen.
right? Yeah.
Yeah. And due to one dimensional, it is not possible. That's
Yeah,
why
and
it will be.
yeah, you can never found degeneracy in one dimensional quantum system.
Yes, yes.
That is
Due
not
to
possible.
that is only based on principal quantum number.
Yeah, 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 you need more number of quantum numbers to have degeneracy.
Okay,
So,
okay, sir.
and you can only have more number of quantum numbers other than one if you go from one dimension to two dimension. Even in two dimension, you will have degeneracy or any other higher dimension. So
So
in one,
number of degeneracy is a uh, 3C3, sir. 3C3.
that I have to look. I'm not sure about that. Like, uh, yeah, I mean, or you can just logically draw out like what could be. You can just increase your NLM values and see. Yeah,
For n equal to 1, we have minus 1, L minus 1, 0, minus plus 1. Is it correct?
sorry.
Like this, we have to.
Yeah, 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 you can increase, like you start from the lowest one and you increase
Uh,
one of the quantum number and see.
okay.
And also, like, it is not necessary that every quantum system will have degeneracy. Suppose, as I said here, this three-dimensional quantum system, three-dimensional infinite well, was cubic type three-dimensional well. If it was
Yes.
rectangular, it cannot you cannot have the degeneracy, because here what happens, all the L which I'm writing down here, so in all the three
Mhm.
dimension of the cubic well has the same length value, which is L. If all of the three has different L value, so if this is Lx, Ly, Lz, then you may not have the degeneracy. So this
In,
will not show
in
any.
cubic case.
Yeah, in cubic case you will have degeneracy.
In cubic case, we have degeneracy. Okay.
Yeah, yeah, yeah. Right.
Thank you, sir.
Yeah. So okay. Okay, maybe the last, we had one more question. We can quickly go this one, and then we can end the session. So Um, uh, okay, so last what we have, so we have a instead of a one dimensional infinite well, we have one dimensional harmonic oscillator system, like linear harmonic oscillator. So um, so now you have again, we are given with the initial state, which is again composed of two eigenstates of the harmonic oscillator, which are zero eigenstate, and the zero is the lowest or the ground state of the harmonic oscillator, and one is the first excited state, and B1 and B2 are its corresponding, like uh, transition coefficients or transition amplitudes, whatever you like to call it. Sometimes they are known expansion coefficients. So yeah, so 0 and 1 are the ground and the first excited state. Then again, find the expectation value in the state side. So again, the same exercise we have been doing. So once again we can do it. So before that, just let me give you some uh, like brief idea if you have forgot about the quantum harmonic oscillator. So in quantum harmonic oscillator, one dimensional harmonic oscillator system, you have so you have phi n, the is denoted as or it, the again, this eigen state solution is again, you can found from again, you can get it from the uh, by solving the Schrodinger equation, where you have to put the potential to be so for your harmonic oscillator, your potential is basically half m omega square x square. So yeah, so this is your potential. If you use this potential in your Schrodinger equation, then you will find this kind of solutions, the for the harmonic oscillator. So this will be alpha n square x square hn alpha x. So where this is something known to be as Hermite polynomial. So here the solutions are not going to be as simple as you found in uh, one dimensional infinite well. So so here you will encounter some special polynomials, and again this alpha is something that is given to be m omega square over h. Like I'm not sure about that, this alpha, but like this is something the form or appearance of the wave function would be. So it would have something like a Gaussian type wave function, which is the first exponential factor, and a Hermite polynomial. So uh, yeah, uh, and basically in so this you can also Dirac, in Dirac notation you can denote it as ket n state, so otherwise known as number state. And there are something also known as there are something called ladder operators in harmonic oscillator. So and and if you use this ladder operators, it makes a lot of computation very easy. So what does this ladder operators do? So if you have a so these ladder operators are basically annihilation operator and creation operator. So uh, uh, yeah, so this is your uh, annihilation operator, and this is your creation operator. So if you use let's say creation operator, uh, so this is your creation operator. If I act it on nth state, it will take you to the next state, so with some coefficient value. And if I act annihilation operator on n state, it will take me one level down to the uh, uh, to the lowest successive level. So yeah, so that is their work. So now here what we can do, let's say like I think in the question itself, it is mentioned that use this position operator. So to calculate the expectation value of the position or the displacement. So position operator is itself given in terms of ladder operators. So using this we can calculate. So again, the expectation value, by definition, it goes something like this. So the state is given to be a linear combination of uh, ground and first excited state, as we have seen in the problem. So thus, let me write down the state here psi, which is given as b1 0 plus b2 1. Okay, then so again, if you take the complex conjugation, you will find out b1 star, then bra 0 plus b2 star, then bra 1, then operator x acting on b1 ket 0 plus b2 ket 1. And this, so first you operate x. So let me write down as b2. So x is written to be is given as given in the question. So h bar over 2m omega a plus a delta. So again b1 0 plus b2 1. So I can pull out this overall common factors, and so I have b1 star 0 plus b2 star, then a plus a double plus b1 0 plus b2 1. Yeah, so you just yeah, you can find out one by one, like what would be each term giving you. So first, if you do b1 star 0 a, then so b1 star b1, so I'm taking this and this, then I can take b1 star b2, again yeah, 0 a and 1. So so there will be many such terms. So let me write down the other ones. So b1 b2, yeah, so like if you keep on doing this, so let's say when a acts on 0, so it will basically give you 0. The first term will itself will go 0. So when a acts on 1, so this will give you again 0, because it will basically root 0 0 from this definition of the ladder operator for the annihilation operator case. So again, this term will be 0. So again, you will find multiple systems. If I write down only the terms which will be uh, yeah, so you'll find these terms going 0, like maybe I'm like, let me write it down directly, the non-zero terms. So the non-zero terms will be uh, b1 b2 uh, uh, just let me check if the b1 values are the real values, or let's say so b1 b2 are real. Let b1 b2 are real, so which means b1 star equal to b1 and also b2 star equals to b2. So maybe this is something missing in the question, but anyway, so it will give you b1 b2. If I take right here, then b1 b2, it will be 0 a 1. So this term will give you non-zero contribution, and there will be one more term that will be b2 b1 1 and a dagger 0. And then again you will have other terms will have some 0 contribution. So So finally you have b1 b2. So when a acts on 1, so when a acts on 1, it will give you um, 1 times 0 state. So when uh, this a dagger operator acts on 0, so this will give you 1 times uh, cat 1 state. So that means you will have b1 b2 plus b2 b1. So that means your expectation value will be just simply 2 b1 b2 h bar over 2m omega. So this is just a bit simple algebra. So okay, right. So yeah, this is what the expectation value you will have if you just simply use this position operator in terms of ladder operators. So maybe I've gone through this one maybe a bit quickly. If any problem, please just let me know. Like any question right here. So you have to just use this algebraic definitions right here, and then you just keep doing the algebra in the expectation value. So this is given to you. The position operator can be written in terms of the sum of operator a plus a dagger operator. So any questions, anything not clear in any step here, or also anything before, uh, or anything else you want to ask, anything?
Hello, sir.
Yeah.
I wanted to ask, would there be regular classes like this session?
Regular classes in the sense like every week we will have a live session. So like whatever problem you are having, you
Okay.
can let us know, we can discuss right here. We'll try to solve some particular important problems related with that particular week's content, and also the assignments of that week's content. So probably you can access all those lecture videos and assignments already before we are having this live sessions. So, and yeah, I hope you can able to access them, so you can start like going through those lecture videos as soon as possible, so you won't have problem in discussing or any asking any other doubts like during the live session. So yeah, so
Okay, sir.
okay, yeah, anything else, anything like you want to ask, or anything that was completely you went black in this discussion today which we had right here, or yeah, any silly thing you missed out or anything not clear, just please you can always unmute yourself and you can ask.
Sir, I have another doubt.
Yeah.
You said about the state can be evolved in like the exponential, right? Uh,
Yeah,
and
yeah,
second question,
yeah, right, yeah, this one, yeah, yeah,
yeah,
with the evolution operator.
basically yeah, basically the state is evolved,
uh,
but can we do it like operators evolve, because both are same
yeah,
thing, right?
yeah, yeah.
Can we
Operator
describe it
symbols
like
is again another like Heisenberg picture again, which you will learn in this quantum mechanics course. So here, as we have like as we were evolving these states, so in case of operators, like you can evolve something, this operator O of t from like some operator you will have of this kind, the similar type of operator which we have used, the evolution operator. So this will be O of 0, and so something, yeah. So you will have this kind of, this means just simply um, this u dagger of 0, u dagger of 2. So this is evolving operator. So So this is we are trying to evolve states, and operator will be this. So this can be any operator, or this uh, calligraphy O. So yeah, this is what you trying to say, right?
So which method would be easy to do that?
So these are the operators, right? So this can be like what I mean, if you have like some momentum operator or something, you can evolve it using this evolution operators. So this is done in Heisenberg picture. So this is what we were doing was Schrodinger picture, evolving states. So this like these are the operators, and if you want to evolve these operators, this is the operator at t equals to 0. This is the initial moment of your operator, and if you want to evolve it to some time t, then you have to use this evolution operators. You have to send this evolution operators uh, among the you have to sandwich this evolution operator, uh, where you will keep the actual uh, physical operator in the middle. So the entire like you will have more like thorough discussion on this type of computation again when you will go to time dependent perturbation theory in this course, maybe after 1 or 2 weeks you will have that. So this is what you want to know about evolving operators instead of state, right?
Yes.
Okay. Yeah. So you'll get more on this maybe in the next coming sessions. Like you can find the lecture videos. Like you can first go through that, and then we can discuss more on it. We can discuss some problems as well. So yeah, so other than that, like if you anything, uh, maybe whatever you have till this point, whatever you have seen the lectures or any assignments that I think all of them, all of you are able to access at least the course content like assignments and whatever the lecture videos are uploaded for whatever weeks till now. Uh, okay, so. Yeah, so okay, so if you have any questions, please let me know now immediately, or we can just see next time. So again, we can see tomorrow uh, around this time. So uh, okay, so probably I see there is no more questions, so probably we can end it right here. So okay, so thank you everyone. So we can see again tomorrow.